Thanks for having me, everybody. I'll give you a brief summary and some highlights of this Buildings of Excellence Round 1 winner, Rheingold Senior Housing. If the slides will advance. Okay, so MAP is designing affordable housing in the greater New York City area. And we've been tracking our portfolio over the past 10 years, comparing it to the baseline of code, which is the black line at the top of this source EUI chart. And our BOE winners are logged here with their site and source EUIs and Rheingold seniors. You can see it's from 2019 when we designed it. We are trending. We see this as part of we see the larger trend here from this chart of a progression towards lower source EUI towards net zero operational energy. And we're also tackling the embodied carbon question. So we're committed to this, to reaching those goals, but it's still a work in progress. The senior building has studios and 1-bedrooms. And we are going to talk about, I'm going to kind of touch on how we're balancing sort of not competing, but different aspects of the building with passive house targets. So balancing passive house targets with cost, balancing with embodied carbon considerations, and balancing them with a dense senior building. The site is in the former Rheingold Brewery in Bushwick. And these are our metrics. You can see that when we designed, the code was 2016 and what the EUI would have been for a code baseline building. So you can see how much of a greater improvement the passive house targets are getting us. But this being a dense senior building, and we were targeting FIAS 2015 certification, we aren't quite able to meet the source energy target. All the other metrics, the peak heating and cooling, we're able to meet, but this being a very dense senior building with lots of appliances and plug loads in a small footprint, that is the reason, one of the main reasons we won't be able to certify. Also, if the grid was significantly cleaner, we could also probably certify, or if we've reduced our window to wall area ratio, which is currently at 27%, but that would have been a bit infeasible for this project. Even though we can't certify, we've incorporated all of the quality control measures of passive house into the project, so that we can achieve the lower EUI. This is a quick summary of the thermal enclosure, which is not that much more robust than current 2020 code in New York City. We have adopted a stretch code here in the city, so those R values are getting more robust and more reasonable for what we really need. We might even look again at this R50 roof value. We might be able to reduce that a little bit. We're seeing in our other passive house projects that we're able to reduce that a bit because the form factor is so good, and we have such a internally low dominated building. Another interesting point here is that the air tightness in the code, actually for each component, taken by itself, could meet the passive house targets. But what makes passive house different is that all of these really tight components together have to meet that total air tightness. And we also, don't need triple pane windows usually in these internally low dominated buildings. We would need it sometimes for the comfort criteria, but I think between the standards and the different versions of the standards, that comfort criteria is changing. So we like to balance the embodied carbon of that triple pane glazing with the operational and comfort criteria. So most of the time we don't do triple pane. one of the wonderful things about Passive House is the increased relationship and the deepening of the relationship between MEP engineers and architects. You know, they really need to rely on our Passive House envelope to right size their equipment. And that makes for a better collaboration. So this project will be almost all electric. We do have an alternate for using a heat pump to make the hot water, which is becoming a pretty standard consideration in most of our projects. We have a fair number of them in the office with that air source heat pump. So balancing cost with Passive House, it really depends on what baseline you're looking for. So for this project, we were targeting the same systems that you would need for Passive House, the ERVs and the VRFs. And in our typology, we have enterprise green communities, which is very common in the States for affordable housing, and especially in New York City, where we have to be 15% better than code in terms of cost of our energy use. So with a great baseline in those systems, we knew we wanted to have a healthy building. So VRFs and ERVs were critical for that. We had this sort of list of all of the specifications that would be involved in addressing energy use. So all of these specifications, we would have to tweak slightly between the sort of baseline, which is a little bit better than code, and a Passive House alternate. And we gave this Passive House alternate to 4 contractors. And they came back with a price difference of only 1%. And the biggest savings was in that relationship between the envelope and the systems, where the condensing units for the VRF actually were able to be 20% smaller in the Passive House option. So that was a critical savings we were able to capture and show actually the annual cost savings, which convinced the client to go to Passive House. This is our typical floor plan. We have these interlocking studios, which I'll show you in a second, a little bit greater detail. We take advantage of the space behind the tubs where 2 bathrooms come together to run our vertical ERV shafts. We often do this design move in our senior housing to have a nice lounge at the corner where the stair and the elevator are, which actually contributes to part of our zoning requirement for senior housing to have these amenity spaces. Of course, it's important to make sure everything is stacked nicely. You don't have a lot of offsets. That saves operational and embodied carbon. And here's a view of those interlocking alcove studios. With senior living, it's critical to try to give a studio apartment in particular a variety of spaces so that people can live perhaps with an attendant, or 2 people can live in a studio together. Another important aspect I wanted to mention here that's required by enterprise green communities, this affordable housing baseline, is apartment compartmentalization, which reduces stack effect in a large building like this, and also contributes greatly to the healthy interior of the apartment, reducing smells from your neighbor. And it's actually pretty much required by code to do anyway. It's just another kind of quality control aspect that, you know, we're also kind of the same concept with the exterior envelope. When designing the VRF system with the evaporators in the units, the condensers on the roof, there are a lot of considerations when using them in this typology that you want to think about. You know, normally the landlord pays for heating. How do you bill for cooling? Because the units are, the condensers that use the most power are on the house meter. The evaporators just use a little power for the fan in the unit. So normally we have like a third-party billing system that does the cooling, or the owner pays for cooling, which is about $40 a month or so, depending. Another consideration is to try not to to give as much flexibility in terms of the mode of the unit. So in heating or cooling, and we do that by creating zones by facade. So for the facade, for the environmental exposure, you really want to watch quality control of your condensate during construction. Those pipes can, if they get kinked, they can cause issues. And you can place your evaporators close to the exterior or in a little bit. And we use wall-mounted ones instead of ceiling-mounted ones because we have pretty tight floor-to-floor heights in our typology, and usually so we don't have a drop ceiling to place them in. And I'll get into it a little bit more, but the refrigerant distribution is a lot more efficient in this sort of vertical riser condition. So this is our top floor, showing that we have an occupied roof on the west side of the building. So in order to get from the evaporators to the condensers, which are all located on the east or the right side of the building, you have to have these offsets. And so this is kind of showing this concept of how much more refrigerant and how much more refrigerant lines you're adding if you're not really thinking through early in the design how the evaporators are connected to the condensers. This is another project that is exploring heat recovery as an option, which is something that is perceived to give more occupant comfort, or but in the end, we find other ways of doing this, of giving that control by zoning the facade. And it doesn't, in energy models, it doesn't save that much energy. And you can see how much more refrigerant and potential for leaks there is with that kind of horizontal distribution. This is the cladding design, which is using the thermally broken girts and spacing them according to the size of the mineral wool insulation, so that it's quicker to install. There's less penetrations attaching the insulation to the backup wall, and it's thermally broken. And the cladding design, the spacing of the windows is based off of, like the space between the windows is based off of the size of the cladding to minimize the amount of cuts of the material. Actually, this product is the waste cut from their other manufacturing processes. And the design here is to not have to create shop drawings, but just a pattern, so that makes it easier and cost effective. A lot of our structures are block and plank, which is CMU block and precast planks that span like about 30 feet. But in this building, we have, you might have seen in the plan or noticed that we have a single loaded corridor where the lot is really shallow. So we have this sort of steel framed facade where we have some public space next to that lounge. And that steel frame facade kind of gives some, we really worked hard to keep that steel off the face of the building so that we could give more, give a nice clean surface for the air barrier to be applied to without a lot of ins and outs and things to overlap. And so it's difficult with this. The structural engineers really like to line up that steel I-beam with the center of the CMU of a parapet or the walls above, for example. You can kind of tell, I'm sorry I didn't draw a center line, but they're offset. This is a view of our sill and jamb using the same size. The size of the panel, actually, it fits perfectly with the jamb of the window. So we were able to cover the jamb with that panel. And lastly, just a short note about embodied carbon. You've probably seen that we're using mineral wool, which has lower embodied carbon than other foam choices for rain screen. But this product we're extremely excited about. It replaces two products, the gravel layer and the subslab insulation, which could be typically foam. It's a recycled glass aggregate. It unfortunately has the word foam sometimes in its name. but its low toxicity. It has about an R2 per inch. And on this project, we actually needed an SSDS system, which subslab depressurization. So we needed to have some airspace in that gravel layer in order to control the vapors so that they wouldn't get into the building. So they're sort of funneled into these tubes and then out through a fan on the roof. So we went through the Office of Engineering remediation to get this foam glass approved as instead of the gravel layer, which would normally provide that airspace. But at the pipes themselves, we actually need to have that true gravel around the pipe, and then we can have 2 inches of the foam glass above that, and everywhere else the insulation of the foam glass.